Read the mind of the model and understand the thought process. So a human AI researcher can't understand the black box, but the black box can understand the black box. All right, we're making progress. Hey everybody, the new O1 models are here. By now, you've likely seen how the O1 models are a paradigm shift from the GPT-4 models. So how did OpenAI do it exactly? Well, in typical open fashion, they published a research article where they shared basically nothing.
Very demure, very mindful.
I've spent the last few days piecing together the breadcrumbs from OpenAI, read multiple research papers across all the LLM companies, decrypted tweets from OpenAI researchers and other industry leaders, looked into Q-Star, and cross-checked with fellow AI industry friends. And what I've put together is the most detailed and technical explanation out there. So today I'm going to cover 3 topics. First, the difference between O1 and GPT-4 models. Next, the reinforcement learning algorithms that make the reasoning possible. Then, how O1 got trained. And lastly, the game-changing impact of longer compute for inference. My name is Tam, and I'm a machine learning engineer, and I've worked on projects like the Apple Vision Pro and robotic arms, particularly with a focus on computer vision models. So that's why today I'll be treating this analysis with just as much rigor while keeping it easy to understand. But hey, what are our human change of thoughts for, if not this? So let's get into it. All right, so let's first start off with the difference between the GPT-4 models and the O1 models. Both of them come in 3 stages: pre-training, post-training, and inference. But you'll notice that the post-training for O1 is a bit longer, and the inference is correspondingly also a bit longer. Well, that's because the post-training for GPT-4 has 3 subcomponents: fine-tuning, instruct-tuning, and reinforcement learning with either human feedback or AI feedback. Whereas the post-training for O1 has those 3 same ones, but has an additional reinforcement learning step to be able to work through a tree of thoughts with the rumored Q-Star method. Because reinforcement learning is such a big aspect of O1's training, I'll be expanding on both of these reinforcement learning methods today as well. But first, to briefly recap what each of these steps are for pre-training, that's when you feed the language model the entire corpus of data. So that can include anything that you've scraped from the web, books that have been published, news articles, business reports, and so on and so forth. The model will then pick up on the patterns within the data and thus form an understanding of language. And also inherent to language, the model will also obtain some reasoning abilities. Not because the model's explicitly been trained to do reasoning, but because in order to be proficient in language, you do need to make sense to some extent. In addition, the model will also memorize or compress facts into itself. And through this, GPT-4 has achieved general knowledge. And if you want knowledge that is more specific, that's what the fine-tuning step is for, when you feed it data from a specific domain or proprietary data. Now, all this data and knowledge so far is great, but it's not going to be very helpful until the model can take instructions from you. And that's what instruct tuning is for. So that when you tell the model, summarize this book for me, it'll actually provide you a summary rather than just doing some other arbitrary language thing. And this is what will enable the language model to become an assistant as well. But we don't want just any type of assistant. We want one that provides us good and safe responses. And here's where the human feedback comes in, so that we can guide the model on what a proper and appropriate response can look like, so that the model can become human aligned. So that basically when you ask GPT-4, how do I create a bomb or how do I harm someone, it's not going to answer you. And this is what allows GPT-4 to have that very polite and human-like response when it responds to you. So that brings us to the end of training for GPT-4. And all these attributes that are present in GPT-4, O1 also has. But now, of course, we have our little extra super secret strawberry sauce, which allows the O1 to be able to produce multiple possible outputs and then also reason through all these outputs to give you the best possible one. And this is what equips O1 with reasoning. We'll expand a lot more on this today as well. Moving on to inference, you'll notice that the inference here is longer than in GPT-4. Let's understand why that might be through these visual diagrams. So this here is from a recent research paper that illustrates the 4 possible ways an LLM can problem solve and then respond to you. First up is the method that we're most familiar with, a simple input to output prompting, where the response is meant to be quick and there's not much additional thought processing happening in between. Next up, we have chain of thought, which is when the model can break down its answer into step by step until it arrives to the final answer. And these 2 approaches here is what GPT-4 is currently capable of. But note, just because you can ask GPT-4 to break it down step by step for you, doesn't mean that the chain of thought here was accounted for or related to the answer given here, which means that these two could have completely different answers. In other words, these two streams here could just be two different streams of bullshit. So long that they sound coherent, of course. And as for this next method here, it's like you're taking your chains of thought and then just rolling the dice 3 times and seeing which number it lands on the most. And while this may improve the model's chances of getting the correct answer, it certainly isn't an elegant approach. So that's why now, in an attempt to be more elegant, the flow of thoughts now is more intricate, where the thoughts can connect with each other across different chains of thought and also through different levels. And this tree of thought here is what O1 is able to create and also reason through in order to provide you that final answer that is the most correct. So these approaches here, where some are quicker and more instinctual, whereas some are slower but more thorough, is also referred to as System 1 and System 2 thinking. These concepts are actually original to this book right here, Thinking Fast and Slow, which I just so happen to have, but don't ask me if I read it all or not. Overall, GPT-4 models can be described as doing System 1 thinking, and by thinking so quickly and instinctively and with little to no effort is also what makes GPT-4 vulnerable to creating hallucinations. O1 models, on the other hand, are doing System 2 thinking, where it's definitely thinking slower, but that's because it's putting more effort into its thoughts to be more logical and to be more rational, hence its reasoning capabilities, which allow it to make more complex decisions, which in turn lead it to be more correct more of the time. And that there reflects how inference is done differently for GPT-4 and for O1. So overall, GPT-4 prioritizes coherency over correctness, which is why it suffers from hallucinations. But on the upside, it is a multimodal model where the GPT-4 models can handle both text, audio, and images. I have another video where I talk about the difference between GPT-4 and 4o if that interests you. As for O1, it prioritized reasoning and being correct more, though it won't always be correct because that's some level 5 stuff. We're only at level 2. And so far, O1 is only a single modality where it can only reason through text. But in AI's research article, they did hint towards vision capabilities in their official O1 model. So I'm going to be very curious to understand how O1 is reasoning through images. So with that, we've covered how GPT-4 and O1 are designed while covering their similarities and differences. Next, I'm expanding on these 2 reinforcement learning steps here. All right, so I'm going to first lay the groundwork for reinforcement learning. And like any other learning algorithm, like supervised learning and unsupervised learning, you have an input and then also a desired output. But instead of a deep neural network in between here, you have this framework instead, where you have an agent within an environment, and that agent has a set of actions and behaviors that it can choose from, which influence the state of the environment, and correspondingly, a reward or a penalty will be fed to the agent to know if it did the right thing or the wrong thing. And of course, the new state of the environment will also get passed to the agent to influence its next iteration. And then you have your policy model and reward model, which inform what type of actions are possible for you and what types of rewards you can get for it. And because these are models, some questions that need to be answered are, what is its mathematical function? Or if it's a neural network, how was it trained? You'll also need a reinforcement learning algorithm or technique for this framework to define how the agent should explore the environment or how it should learn from the rewards, and in what way to make its decisions to maximize its long-term success. A common example of this would be if your agent was a computer program that was learning how to play chess. So the environment would be a chessboard and the rules of chess. The policy model would say which moves are possible for you to make. A pawn can move 1 step forward, or a knight can jump like an L. And depending on what move your learning agent makes, it will either receive a positive reward or a negative reward based on whether one of the opponent's pieces have been captured or the opponent captured one of your pieces. Once that happens, the learning agent will see the new state of the chessboard, and that will inform the next iteration and the next cycle for its learning process. So that ideally, after this training via reinforcement learning, you have an agent that knows what moves to make in order to win a chess game. All right, so now that we have the fundamentals to reinforcement learning, we can now take a look at reinforcement learning with human feedback or AI feedback. So it has a similar layout where now in the context of GPT-4 models and O1 models, your input is going to be a prompt and your desired output is a coherent and safe response, where your policy model is now a neural network. So how was it trained? Well, a data set had to get created with input prompts and desired output responses. And these here were provided by the human to model what a nice, coherent, and safe response would sound like. And then you use this data set to fine-tune your GPT-4 or O1 via supervised learning. But based on the response given by the model, in this case it's action, how do you know what reward to assign it? Well, the reward model here is also a neural network where you have to train it as well. And you do that by creating a data set where for every one prompt, there's several possible outputs to it. And these output responses are going to get ranked by a human from best to worst. And this ranking system is going to teach the reward model how to assign a numerical value for the reward right here. And lastly, to navigate through all these components, you need to have this reinforcement learning algorithm, which OpenAI has chosen to be proximal policy optimization. I won't explain it here today since this video will already be long enough, but OpenAI did publish its research for this one. All right, so that was reinforcement learning with human feedback that teaches the model how to make coherent and safe responses for the input prompt. And human feedback was involved with training the policy model and the reward model. It's also gotten the name AI feedback because now with our advanced LLMs, we've been able to replace some of the human work with AI work. And now for our next reinforcement learning algorithm, the super secret strawberry sauce. Here's where the model learns to reason. So we're going to turn up the complexity a little bit, which you might have already noticed with the two reward models here. Here, the input is a prompt or a problem, and your desired output is the most correct or the most reasonable chain of thought from a tree of thoughts. Now that's quite the mouthful, and you'll see how it's distributed over all the components here. Both your policy model and your reward models are going to be neural networks that you need to train. For the training of your policy model, you're essentially fine-tuning GPT-4 to output the next step in your solution for you. So how that's going to look like is if you give it an input problem from the math data set and a solution with steps 1, 2, and 3, you're going to ask GPT-4 to output step 4 of your current solution. And based on that step 4, if it was the final answer, then the outcome reward model will decide your reward. And if step 4 wasn't the final answer, then the process reward model will decide your reward. Now your reward models here are also neural networks, each with their own way of getting trained. The process reward model was trained via process supervision, and the outcome reward model was trained with outcome supervision. Training the outcome reward model is relatively straightforward since a final answer is either correct or incorrect for a math problem. So for here, you don't really need a new data set or any additional labeling work from a human. The process reward model, on the other hand, isn't as simple because there's many ways the steps of a solution can look like. So here now, you need to involve some human annotations to label whether a step of a solution is either positive, negative, or neutral. The human labeling for something so abstract and so dense is obviously going to be very expensive. So that's why you're going to split the labeling and learning process of this into 2 phases, where phase 2 will also include active learning to further reduce the labeling effort. Now, this is just a high-level overview of how the process reward model is getting trained, but it's such a key part to this reinforcement learning algorithm that I'll be expanding on how this was trained here in the next slide as well. But before we do that, we need to talk about the reinforcement learning algorithm that drives this whole framework here. And this is where that alleged Q-star algorithm fits in. And while there's no official publication on Q-star yet, it is understood to be a mix of Q-learning, A-star pathfinding, and Monte Carlo tree search that enabled the learning algorithm to navigate its tree of thoughts by doing look-ahead, backtracking, and self-evaluation. And with that, now you have a high-level overview of how the reinforcement learning algorithm that drives the reason capabilities of O1 works. Now you understand how its reinforcement learning algorithm was designed and what its key components look like and how they were trained, and the algorithm that drives all of this. Of course, now when you break each of these components down further, it's going to get a lot more complex, which is what we're about to do next. All right, if you're still with me here, I commend you because I know it has been so much so far. But nobody said that creating an LLM capable of reasoning capabilities was easy. So we continue. So let's talk about how O1 was trained. Specifically, the generator, which becomes its policy model, and then phase 1 and phase 2 to train the process reward model. And the information I present here is from a research paper from OpenAI and Ilya Sutskever, published just 1 year ago. So as an overview, we have these 3 stages here. Now, let's break it down some more. First, for the generator, you take an input problem from the math dataset and a set of instructions for it to provide multiple solutions to this input problem, each in a step-by-step format. and you feed the instruction and the input problem to GPT-4, which will then give you multiple solutions in a step-by-step format. Now, some of these are going to have a correct final answer, and some of them will have an incorrect final answer. You take only the solutions with a correct final answer to build your data set with it. So that now your data set will include input samples and target values, where the input is a math problem and the target is multiple solutions in a step-by-step format with the correct final answer. You take this data set and you use it to fine-tune GPT-4 for one epoch, which will give you this GPT-4 star I've arbitrarily named to indicate that it's a specialized version of GPT-4 that can generate solutions in a step-by-step format. And that there is how you train your generator and therefore your policy model. Now moving on to phase 1 to train the process reward model. And here the generator will already output multiple solutions for you in a step-by-step format. It doesn't need that additional instruction because it was already trained to do so. Now these solutions, which are also more likely to have a correct final answer, where for each of these solutions and each of the steps within the solution and each of the completions within the step, a human will then assign a correctness label of positive, neutral, or negative. Now that again was a mouthful, so we can look at this visual diagram here to understand that a problem has multiple solutions, and each solution will have multiple steps until the last step is the final answer. And in each of these steps, you're going to have multiple possible alternatives to express the step, and that's referred to as a completion. And from each step, you're going to choose one of the completions here in the bolded line, which will then influence what completions you get available here. And then you're going to again make one selection, which will influence the next set of completions that you get here. Now, completion is an interesting name to call what's essentially just an alternative, but interestingly, the term completion is something that's also used within the OpenAI API. So yeah, this is how you can think of a problem and its tree of solutions when I use the words like solution, step, and completion. And this structure for the data set was defined within the data set that OpenAI made publicly available called PRM800K. And this data set for the annotations done in phase 1 has annotations at every single step and for every single completion. And that's what we refer to as dense labels. And the human labeler would annotate it with positive if the completion was a correct step, negative if it was an incorrect step, and then neutral if it was neither correct nor incorrect, and it just didn't really help progress the solution of the problem. So now back to our flowchart. After a human has provided those labels to each of those solutions and its steps, you can now use those labels to put it into your new data set, where your input is now going to be a math problem, its corresponding solutions, and all the steps to the solution. And it's going to have labels for positive, neutral, or negative for each of the completions in those steps. So that's why you call it dense labeling. And this is what makes up phase 1 of the labels. Now you can use this data set to train your first reward model, which is how you're going to get your phase 1 process reward model. Now incorporate this reward model with this policy model now into the reinforcement learning framework, where after some reinforcement learning training, you're going to get your baby O1. They're your very first version of O1. And thanks to the dense labeling here and the reinforcement learning done, this baby O1 is going to have some reasoning capabilities already, but we want more reasoning capabilities, and we don't want to annotate as much anymore because that's time consuming and expensive. So that's what brings us to phase 2. All right, so for phase 2, you start off the same way, where you give it an input problem from the math data set, and you feed it now into your new baby O1, where the solutions it spits out for you are, again, multiple solutions in a step-by-step format, but this time, since they came from baby O1, they were made with some reasoning, and therefore the steps within them are going to be more likely to be correct. With that, you feed the solutions into an active learning selection strategy, where you filter for the solutions that are most likely to fool the current process reward model. And by fooling, we mean the solutions that have the wrong final answer, but yet still have the most convincing intermediary steps. We filter for these ones because these steps is what the PRM is messing up on. And so getting labels for these particular solutions here is going to be the most informative in training the reward model to be better. Once your solutions have been filtered, these are the traits that it'll have. very highly rated steps and reasonings, but yet the incorrect final answer. And these are what will get annotated by the human. But this time, you don't want to do dense labeling as before because that's expensive. Here, you're doing sparse labeling. So that would look like, instead of labeling positive, negative, and neutral for all the completions of all the steps, you only do the labeling of the first completion of each step. And you do that until you encounter completion that is incorrect. And only when that happens do you look at all the available completions of that step and then provide labels to that. If all the completions just happen to be incorrect and therefore get a negative labeling, then you end your labeling of that solution right there. You don't go any further. So as you might have noticed, the labeling approach for this isn't intended to get the final correct answer. It's more intended to rule out bad steps. All right, and with the human labeling here complete, this now forms the phase 2 labels of your dataset, where you again have the same input, problem, solutions, and steps as before, but now your labels are sparse. Now you take this dataset and you fine-tune your current best reward model with it. In this case, your current best reward model is the phase 1 PRM here, which will then give you a phase 2 PRM. And just like before, now you can take your PRM here and your policy model here to now integrate it into a reinforcement learning framework. Let that train for a bit for you to get your baby O1, which has even more reasoning capabilities than before. Now it's even better discerning the steps of a solution as being correct or incorrect. And we like where this phase 2 is taking us so much that we're going to repeat it 10 times over again. You're going to iterate over the training of baby O1 over and over again with the same active learning strategy and the same sparse human annotation for you to finally get the O1 model that we have learned about today. And as you repeat this over and over again, the goal is to be less able to fool the process reward model because you want a smarter reward model. A reinforcement learning algorithm is really only going to be as good as its reward model. So with that, now you know how the policy model and the process reward model was trained for the O1 in high detail. All right, last item. And if you've made it with me this far, you are a superstar. Here, we're going to talk about the plot that OpenAI put at the very top of their research article. And there's a good reason why, too. So let's take a look at the plots here, one for training and then one for inference. You'll notice that the plot is linear for the accuracy, but then logarithmic for the compute time. And for this linear relationship that they have here, it means that for every linear improvement in accuracy, you need exponentially more train time compute to achieve that linear improvement. So basically, the further you extend your compute time, the returns that you get on your accuracy are going to be diminishing. And at some point, it's not going to make that much economic sense anymore to get that 1%, 2% improvement in accuracy. And this issue of diminishing returns, as captured by this linear relationship here, is actually just another example in which the neural scaling laws apply. The neural scaling laws basically say that no matter how much you scale up your model size, or your training time, or the amount of training data that you have, you can predict how much of an improvement you're bound to get. They're all going to falter to this linear line on a logarithmic plot. And they're left wondering, is there any way to cross past this linear line? Well, now they have, by extending the compute time during inference instead of just training. So previously, the AI and ML community was fixated on toggling the training time because that's really all you could do, right? Because previously, the inference was a simple input to output and you couldn't really iterate. Now, O1 is able to spend more time creating that tree of thought. The more time that O1 can spend navigating and parsing through that tree, the more likely it can provide you a correct answer. And so with that, with O1's reasoning capabilities, for the first time ever, you see the birth of the concept of test time compute. Again, you have accuracy on a linear scale and then test time on a log scale. And once again, we see a linear relationship. So that's one significance, that the neural scaling laws seem to also apply to inference with its test time compute. And the other even more significant impact of this is that your model is now no longer subject to those diminishing returns as previously thought. So basically what this is saying, you can take your model that's been trained for the longest and has the best accuracy, and its performance won't end there. You can extend it even further by just inferencing for longer. You're essentially breaking through the neural scaling laws that the community was so long plagued by. This opens up a whole new realm of how much juice that you can squeeze out of your trained model for it to get even a better accuracy. This is really meaningful for the AI industry because now it means you don't need to allocate that exponential amount of training time just to get that 2% improvement in accuracy. You can get that 2% improvement in accuracy a lot easier by just spending more time in inference now. It's less expensive and less time consuming than in train time. How much that trade-off is between train time and test time, we don't know yet because OpenAI decided to make this plot here very ambiguous. It only reveals to us the linear relationship that exists in training and in inference, but not anything beyond that. For example, I would like to know what training time they kept fixed so that they could run their inference time test on it. This is actually one of the many issues that I have with the plots and the evaluation results that OpenAI shared with us. I actually find that OpenAI made the plots and the evaluation results more ambiguous than they needed to be. But overall, the main point still holds that now not only training time is subject to the neural scaling laws and the issue of diminishing returns, but also the inference time is too. But with the combination of these two exhibiting that linear relationship is now how they together can break out of the neural scaling laws and therefore save an exponential amount of train time to get that 2% of improvement. And that's all. And that was a lot. I hope it further clarified the ambiguities that OpenAI puts us through and keeps the conversation open on the current machine learning and research approaches. With OpenAI DevDays just around the corner, this breakdown hopefully makes you more knowledgeable going into it. If you found this video helpful, give it a like and subscribe for more content on AI and ML from a machine learning engineer herself.